Apologize for that. My document camera froze up there, so we'll continue where we left off. We were just finishing conceptual question number 2, saying that when you have the high heels on, the heels will sink in because you have more of your weight located there, and it has a much less surface area and therefore higher pressure on the ground, and so you have that ability where the shoe will sink into that softer ground. Again, it's the pressure determining whether or not that ground surface gets indented or pushed into in this case. The third and final question, this is kind of your worst case scenario survival guide question, is what would you do if you ever came across a situation where you found yourself trapped on thin ice or having to cross thin ice? And most people have probably heard of or seen something like this. In fact, even polar bears know how to do this instinctively because, of course, they live in an environment that has a lot of ice and trying to maintain, their stability as they cross the ice and things like that. So if you had to cross thin ice, the one thing that you really don't want to do is run. If you run, only one foot's in contact with the ground at a time as you're running, and therefore you're actually reducing the amount of surface area that you have in contact with the ice. If you think about the total area of your 2 feet when you're standing on the ice, it's not a whole lot of area. So if you want to decrease your pressure, because the pressure is what's going to ultimately determine whether or not the ice breaks, then you want to spread out your weight as much as you possibly can. You want a large surface area. So in order to do that, you actually want to lay down flat and basically crawl or kind of shimmy your way off the ice, almost like an army crawl type thing, as much surface area in contact with the ice as you possibly can. So you want to lay down flat and crawl. This increases your surface area, and by increasing your surface area, you are decreasing the amount of pressure that's acting on the ice. Thereby making it less likely that you will break through the ice or fall through. So that increases the surface area and decreases the pressure on the ice. Again, coming from that pressure equation, area being in the denominator. So as the area gets bigger, the pressure gets smaller. The force in this case would stay the same because the force is your body weight, and that's not going to change regardless of what orientation you might be sitting, laying down, crawling, or sitting in. So the whole idea behind these 3 different concepts here in these questions is dealing with what happens to those 3 measurements. How do they relate to each other between force, area, and pressure? How can you manipulate those 3 for different situations? Now we're going to take a look at that from the mathematical side a little bit more, and we're going to look into a few calculation examples here. So starting with a 1 meter box, so 1 meter wide by 1 meter long by 1 meter tall. If that's sitting on the floor, you can imagine here's your box. The part that you really care about is just the bottom surface, because that's what's going to sit on the floor. So that's just a square that would be 1 meter by 1 meter. So your area here is 1 meter times 1 meter, and of course that's just 1 square meter. So that keeps that part very simple. Now the other part that you'll notice is that they tell us its mass is 42 kilograms. Remember, mass is not a force. So in order to figure out your force, you're going to have to take the mass times gravity. In other words, find its weight. How much weight is it going to put on the floor? And so 42 kilograms times 9.8 meters per second squared for gravity gives us 411.6 newtons of force. So we have the force, we have the area. Now we want to find what is the pressure that is being put on the floor from that box. So we would have 411.6 newtons divided by 1 square meter. Well, of course, anything divided by 1 is itself, so we get 411.6 pascals as our unit for pressure. Example number 2. This comes from an actual mechanical situation that you will find in some factory floors and things like that, where you have heavy pieces of equipment and you want them to rest on a concrete floor, but the equipment itself can't just sit on the concrete floor directly because of the footprint that it has, meaning the surface area that the piece of equipment would actually touch the floor with is not very big, and so therefore it would indent or start to break apart the concrete. And so they design what's called a force plate to sit underneath it, and it's basically a large flat piece of metal, so that the equipment sits on top of that metal, and then the metal makes the surface area much larger for that weight to be sitting on the concrete. In other words, bringing the pressure down below the threshold that would be dangerous to breaking that concrete floor. So this is an example similar to that. In this case, we're just going to ignore the fact that, yes, the plate itself would also have to have weight. If we bring that part in, the math gets a lot more complicated, and so we're not worrying too much about the reality of that type of situation in the real world, but we are looking more at simply what's the idea here behind manipulating the area to decrease the force. So in this problem, we want our pressure to be 25,000 pascals or less. Okay, so we're going to set it equal to that value, so that way we know that that's the minimum there, or the maximum pressure that we could have, but it'll give us our minimum amount of area. Again, we're given mass. It's in kilograms. So we have a 12,750 kilogram machine, and we're going to need to find the force from that. So again, it's going to be mass times gravity, and that's going to give us our weight, or force in newtons, 124,950 newtons of weight from that machine. And we also know that our pressure has to stay under 25,000 pascals. So pressure equals force divided by area. That means we have 25,000 pascals for pressure. We have 124,950 newtons for force, and we want to find area. Now, mathematically, anytime you have a variable in the denominator, that's the bottom of the fraction, the first thing you should do to be able to solve for that is get it out of the denominator. Otherwise, people end up solving for 1 over that variable instead of the variable by itself. So we're going to actually multiply a out of the denominator. We're going to multiply by a on both sides like this. That gets rid of it on the right hand side, moves it to the left. So we have a times 25,000 equals 124,950. And now to get a by itself, we would be dividing the 25,000 to the other side. So we have 124,950 divided by 25,000. That gets us a surface area, if we round to the 10th, of 5 square meters. With that situation, the biggest key again is mathematically making sure you solve correctly for the thing that's in the denominator. If you have questions with that, you can certainly email me or message me through Schoology and ask about further detail to that math. Now, our third and final example, we have a child and a stool. The child sitting on top of the stool. The stool is a wooden stool with 3 legs, so you can imagine what that would look like. The bottoms of those stool legs have a total area, that means all 3 combined, of 19.3 square centimeters. So we want to find, first of all, what is the average pressure that's exerted on the ground from each of those 3 legs. So in order to do that, we have to think about a few different things. First of all, the total weight. Total weight has to be the kid and the stool because they're both sitting on it. Now you can hear my dogs going nuts in the background. I'm sure a couple people running by on the street right now. You know, our dog's always trying to look out for the safety of the whole neighborhood here, apparently. Our force is going to be 364 newtons times 40, or plus 41 newtons, because we have to add those two together. We need not only the weight of the child, but also the stool that the child sits on. So the total weight that's resting on the floor is going to be 364 plus 41, and that's going to give us 405 newtons of total weight. We also know that the area of all 3 of those legs together is 19.3 square centimeters. We need that in square meters. So just like what we were talking about earlier with our conversions in our squared units, if we are going from square centimeters back to square meters, it's a factor of 10,000, or 10 to the fourth. That means that we would take 19.3 divided by 10,000, or the other way to think about it is we have to take this decimal point and move it to the left 4 places. So that would give us 0.00193 square meters. Okay, and again, you can either move the decimal point 4 places, or you take 19.3 divided by 10,000. You had to be able to do that. Now we're ready to set up and solve the actual question here, the pressure. The pressure would be the force divided by the area, so that's 405 newtons divided by 0.00193 square meters. And when we take that number, we're going to get 209,845 pascals. Now that's not actually the final answer to the question yet. The question itself wanted us to know what is the average pressure exerted on the ground from each leg individually. This is the total pressure from all 3. So if we want to cut that down to be just one leg, we're going to take that and divide it by the 3 legs. So we'd take 209,845 divided by 3, and that will give us 69,948 pascals. That's the value that we actually wanted in part A. So all of this part here is for part A of the problem. In part B, this is going to show you why you don't want to rock on chairs, like classroom chairs or stools or things like that, and why they eventually break. It puts a lot more pressure on them when you have less area that's in contact with the ground. So what changes now if the child leans so only 2 legs touch the floor? Well, the force doesn't. You still have 405 newtons total of weight there. That's not going to change. But what is going to change is the area. The area before in the 19.3 square centimeters was for all 3 legs total. Now we only have 2/3 of that because only 2 of the legs are touching the floor. So what we really need is 2/3 of our original area, which in square meters was 0.00193. That's going to give us 0.00129 square meters. So this is for 2 legs touching the floor instead of 3. Now we repeat the same pressure calculation. Pressure is force divided by area, and so we have 405 newtons divided by 0.00129 square meters, and that will give us 313,953 pascals. So our total pressure has gone way up because we have now only 2/3 of the area that we originally had. So the pressure is greater now on not only on the floor from the feet of the chair, but also on the chair legs themselves. So they have to hold more of that pressure. That's why they get weak and break when you rock on the chairs. That's why teachers often harp on people to, keep all 4 chair legs on the ground at a time. So again, the question is, how is the average pressure exerted from each leg going to be affected? So this is the total pressure. Now we want that divided by 2 legs because only 2 are touching the ground. So we would have 313,953 divided by 2, and that's going to give us a final answer of 156,977 pascals for just each leg on average. So the average has climbed quite a bit, more than double, to be able to accommodate for only having 2 legs now in contact with the floor.